These are the notes on balancing equations in chemistry. You've downloaded the file, you're playing the slideshow, your speaker is on, if you can hear me. The conservation of mass is the underlying law of chemistry. In chemistry, the mass of reactants is equal to the mass of the products in any chemical reaction. This also goes for physical changes. The only time this law is broken is in a nuclear reaction, which we are already done dealing with. So we're going to see this obeyed. This law was laid down by Lavoisier, and we're going to learn about him a little bit later. So basically, balancing equations is what we do in order to obey the law of chemistry. When looking at a chemical formula in a chemical equation, it's important to know what the numbers represent. The smaller numbers written lower are called subscripts. Subscript just means written below. A subscript only applies to the element just before it. In this example, there's a 2, which is a subscript, that only applies to the hydrogen, which is just before it, because there's 2 hydrogen atoms in every water molecule. The oxygen does not have a subscript. Well, it does, but the subscript is 1. That's invisible in chemistry. We don't like to write 1s. Whenever we can avoid it, we leave out the 1s. So oxygen doesn't have a visible subscript. It's an invisible 1. Think of it that way. The coefficient, on the other hand, in this example, it's the big 3, multiplies by the entire chemical after it. So that would really mean 3 of the water molecules. So that means it multiplies by everything in the molecule. So it multiplies by the hydrogen, which is already 2. So you would do 2 times 3 is 6 hydrogen atoms. And then it multiplies by the oxygen, which is only 1. So 3 times 1 is 3 oxygen atoms. So those are coefficients and subscripts. You have to keep those in mind, what they mean, as we are learning how to balance chemical equations. When it comes to chemical equations, sometimes we start with the word equation, telling you what chemicals are involved. For example, this equation shows methane and oxygen reacting to produce 2 products, carbon dioxide and, well, you can probably guess what the last one is. Look down. It's the most famous chemical formula in the world, and it is water, H2O. Okay, so the yellow ones on the left are the reactants, the red ones on the right are the products. Well, then we can rewrite them with their chemical formulas. Methane is CH4, oxygen is O2, carbon dioxide, just like the name implies, carbon dioxide means CO2, and then water, again, everybody knows H2O. There's just one problem. This equation is breaking the law. It is not balanced. Okay, if you look on the left side, notice there are 4 hydrogen atoms in the methane, and on the right-hand side, there's only 2 hydrogen atoms in the water. So that alone means there's a problem here. So in order to obey the conservation of mass, we need to balance this equation. This very reaction, by the way, is known as classic combustion. It's a great example of a hydrocarbon reacting with oxygen. We've got a very simple hydrocarbon, which is methane, reacting with oxygen, producing its typical products. So it becomes more obvious when you look at this picture showing the models of the molecules. You can see easily that there's 4 hydrogen on the left-hand side of the equation, left of the yield sign, and only 2 on the right, so they're out of balance. You can see it in the equation as well. CH4, that's 4 hydrogen there, and on the other side, way on the right, you see H2O, only 2 hydrogen atoms there. So hydrogen is clearly out of balance, but guess what? So is oxygen, because look, now it's more obvious that there's actually only 2 oxygen on the left, on the reactant side, whereas there's 3 oxygen atoms coming out on the right. So what happened here? Did we lose 2 hydrogen and gain 1 oxygen? that just doesn't happen in chemical equations. So in order to fix that, what we need to do is first of all balance the hydrogen. Hydrogen is the first one we start with. So look on the right-hand side where you see that water contains 2 hydrogen. So if I just double that, well, now I've got 4 hydrogen. Okay, that would give me 2 times the oxygen, that's 2 oxygen plus the 2 in CO2, a total of 4 oxygen on the product side. So then I need a 2 in front of the oxygen, a coefficient of 2 in front of the oxygen to balance that off. And now when we see the balanced equation, it should be pretty clear that everything went somewhere. Every single atom on this side, like the carbon, went there. Okay, this hydrogen went there. This hydrogen went there. These 2, I'll do 2 at a time. These 2 must have gone there. All the hydrogen are accounted for. And then we've got 2 oxygen right here. Well, 2 of them went there. And then we've got 2 oxygen atoms right here. Well, the other 2 went there. Notice that I've crossed out everything. Everything on the left side is present on the right in equal amounts. Every element, every atom is accounted for. That's the conservation of mass. I like to put a little check above the yield sign, bing, when it's a balanced equation, when I've double checked that everything is balanced. So now we have obeyed the law, and then the coefficients that we need, well, because we only needed 1 methane, the coefficient is actually 1. We needed 2 oxygen, so the coefficient becomes 2. Carbon dioxide, also, we only needed 1. We don't like to write 1s in chemistry when we can avoid it. And then for water, we put in a 2, coefficient of 2. That is the balanced chemical equation for classic combustion, a reaction of methane with oxygen, producing CO2 and water. Here is a reaction that we've actually seen in a demo. Sodium reacting with water. Remember the demo where I dropped in a small amount of sodium into a beaker full of water, which had a pretty violent reaction. Well, part of that reaction was this part where the sodium reacted with the water, giving off hydrogen, which comes out as a gas, and producing sodium hydroxide. Well, that's a base, which is the reason that the beaker turned purple, because we were producing that product. But is this balanced? Well, there's 1 sodium on the left, 1 sodium on the right. That looks fine. There's 1 oxygen on the left and 1 oxygen on the right. That also looks fine. But look at the hydrogen. 2 hydrogen in water, H2, okay. And then there's H2, hydrogen gas. That looks good. Oh, wait, there's 1 more hydrogen. Don't forget the one that's over here, this hydrogen here. Oh, no, that means there's 3 hydrogen on the right side. So because it's off, because it's not balanced, this requires balancing. To balance this one, it turns out you need lots of coefficients. I'm just going to plop them in. These are the coefficients of the balanced equation. Now, once we've put these in, remember they multiply by the chemicals. Well, now we've got 2 sodium atoms on each side. Now we've got 4 hydrogen atoms on each side. And now we've got 2 oxygen atoms on each side. So now, in fact, everything is balanced. So remember, if even 1 tiny little hydrogen atom is the difference between the 2 sides, it does indeed require balancing. And now this equation is obeying the law. I'm going to show you the technique that is used to balance this equation a little bit later, which is why I just jumped directly to the balanced equation. Hydrosynthesis. A big reaction, very important. In fact, whenever a chemical reaction has a name, it's probably a pretty big reaction. Hydrosynthesis is how water is made. That's what the name means. Hydrosynthesis, making water. If you look at this equation, you can see hydrogen on the left, hydrogen gas, plus oxygen on the left, oxygen gas, producing water on the right. However, there is not an equal number of atoms on the two sides. 2 hydrogen atoms on the left, 2 on the right, that's fine, but the oxygen is not balanced. There's 2 oxygen on the left, only 1 on the right. In order to fix that, well, guess what? We need a coefficient of 2 right there in front of the water. That multiplies the water by 2, everything in the water by 2, including the oxygen. That gives us 2 oxygen on the right side. Well, now we've got 2 oxygen on both sides. Perfect. Oh, great, but we threw off the hydrogen, which was initially balanced. This happens a lot. By balancing one thing, you throw off something else. So now to fix that, well, pretty obviously, on the right side, now we have 4 hydrogen atoms, 2 times 2. We need to do the same thing on the left. And luckily, by doing that to a pure element, putting a coefficient of 2 in front of the hydrogen, it doesn't tamper with any other elements. It keeps everything else in balance. And so with that, we are actually done. And then I like to put a little check mark above the yield sign because we have 4 hydrogen on each side, 2 oxygen on each side. It's balanced. So hydrosynthesis, when it is balanced, is like this. 2 hydrogen molecules reacting with 1 oxygen molecule, producing 2 water molecules. This is a reaction that can have some pretty dramatic consequences. For example, the Great Hindenburg disaster in the 1930s. The reason that we don't float around in those dirigible balloons, those zeppelins, well, that was because they filled it with hydrogen. And of course, hydrogen, when it reacts with oxygen, a little bit of a spark, you get a big problem. Oh, the humanity. Also, when we used to launch the space shuttle, up until about 10 years ago, launching the space shuttle into orbit around the Earth, well, they would use this reaction, put a tank full of oxygen next to a tank full of hydrogen, let them pour together, pour out at the bottom, and little spark, launch you into orbit. So hydrosynthesis is no small reaction. It's one of the most exothermic reactions in chemistry. Remember that the coefficient multiplies by the entire chemical. So again, this would be 3 times 2 for the hydrogen. That would be 6 hydrogen atoms. 3 times 1 for the oxygen. That would be 3 oxygen atoms. When you see something like this, you have to know how to count it up. That is one of the main skills you need when you are balancing a chemical equation. The next skill that you need is to know where to start. When you are balancing an equation, always begin with atoms that are found only once in the reactants and once in the products, but in different amounts. What I mean by this is, if you see an element only found once on each side, but with a different number of them, that is a good place to start. Notice that I have indicated the carbon in this reaction. This is a reaction between oxygen and dextrose, producing carbon dioxide and water. It's another one of those organic combustion reactions, but it's a little different than the one before, but the products are the same. Notice on the left-hand side, how many carbon are there? You can tell by the subscript there are 6. On the right-hand side, how many carbon are there? There's only 1. So how can I make that 6 carbon? What would I need to multiply it by? We need to multiply it, of course, by 6. We put a coefficient of 6 in front of the carbon. So now we've begun the process of obeying the law, balancing this equation. We're not done yet because that just balances the carbon. Well, the next one I would do is something else that's found only once on each side, which is the hydrogen. Notice I do not want to start with the oxygen. The oxygen is found in every one of these compounds. In every chemical in the red reaction, there's oxygen. So that means I want to do oxygen last. If I want to fix the hydrogen, notice there are 12 hydrogen atoms on the left. There's only 2 on the right. So what do I need to multiply that by in order to make it balance? I need a coefficient of, again, 6 in front of the water. So I would say put a coefficient of 6 in front of the water. That gives me 12 hydrogen on the product side to match the 12 hydrogen atoms on the reactant side. Okay, so now it turns out we need to get around to the oxygen. That's the only thing left. If I take the total number of oxygen on the right-hand side, so notice I've got oxygen in both compounds. So if I take the 6 times the 2, what do I get? I get 12. And then if I take this 6 times the invisible 1, I get 6. So what is my total number of oxygen? I actually have 18, and you could say sort of O's. This isn't a proper way to write it, but it's just a note-taking. 18 O's on this side. I need to also have 18 on the other side. So how many do I have? I've got 6 in the dextrose. Notice right here, I've got 6 oxygen. There's a coefficient of 1, so it's 6. And I've got 2 in the oxygen itself. That's a total of 8. So I am nowhere near the 18 that I need. However, if I were to put a coefficient right here, any coefficient I put right there would also tamper with the carbon and the hydrogen. And if I did that, I would have to go back and adjust the ones I had already put in on the right-hand side. So clearly, I don't want to put anything right there if I can avoid it. The good news is I've got a pure element here, and that's a safety valve for getting out of situations like this. So if 6 of the oxygen are already accounted for there, that means I need 12 more. And so how can I make the O2 on the left hand, way over to the left, how can I make that 12? I need a coefficient of 6. So notice it looks like all the coefficients are 6. If all the coefficients were 6, that would mean I could just divide through by 6 and have all the coefficients be 1. That would be a multiple of the balanced equation, but I cannot. Why not? Because the dextrose has a coefficient. Remember, there's nothing written there, so what's the coefficient? It has a coefficient of 1. And of course, 1 is not divisible by 6. So that stops me from dividing by 6. So now we've balanced that equation. And when I've balanced an equation, what I like to do is I like to put a little check above the yield sign just to remind myself that I've done it. The next equation, let's do the same exact thing, maybe go a little faster. We want to start with the aluminum because aluminum is found once on each side in different amounts. There's 4 aluminum on the left. There's 1 aluminum on the right. So what's the coefficient that I need to multiply by? I need to put a 4 in front of the aluminum hydroxide. Well, that takes care of the aluminum. The next thing I want to deal with is actually the carbon. Why not deal with the carbon? The only one I want to avoid dealing with, do you see which one? In this equation, in the green equation, is the hydrogen because it is split up on the right side. Well, there's 3 carbon in the aluminum carbide on the left, and there's only 1 carbon in the methane on the right. So I need a coefficient of 3 in front of the methane. And that sorts out the carbon. So now we've got the aluminum and the carbon all set to go. The next thing we want to deal with is the oxygen. But wait, isn't oxygen already in the same amounts on the 2 sides? Isn't there 1 oxygen on each side? Actually, no, because remember, if you have parentheses, like we have over here around this guy, the parentheses mean that this little subscript outside multiplies by the entire, what is it called? Polyatomic ion inside. So that means 3 times the oxygen and 3 times the hydrogen. So that's actually 3 oxygen right there. Oh, wait, and we have a coefficient of 4. So what's 4 times 3? 12. So we've actually got 12 oxygen on the right-hand side here. So how can we make it 12 oxygen in the water molecule? Remember, each water molecule only has one oxygen. Sometimes you just need the full 12. The coefficient there becomes a 12. That gives me 12 oxygen on both sides. Now finally, we've got to get around to dealing with the hydrogen. We can't avoid it forever. It's the last one remaining. So let's deal with the hydrogen now. Now that I put that 12 in front of the water, the coefficient of 12, how many hydrogen do we have right there on the reactant side? 12 times 2, 24. If we look on the right-hand side, over here with the methane, it's 3 times 4. Well, that's 12. And then, oh, the hydrogen over here, this is tricky. It's a polyatomic ion. It's in a polyatomic ion, hydroxide, times 3. So there's 3, and the coefficient is 4. 3 times 4, that's another 12. So that actually gives me a total of 24 hydrogen on the product side. So by balancing the oxygen, we wound up balancing the hydrogen inadvertently, indirectly. That happens quite a lot. So luckily, we are done with this equation, and I can put my little check mark above the yield sign to remind myself that I've balanced it. The only reason it would not be balanced, if I've got the same number of atoms on both sides, is if I could divide through by a 2 or a 3 or some other number. But notice that's not going to happen, because we can't divide 4 by 3, we can't divide 3 by 4 and get a whole number, so we are done. That is a balanced chemical equation. We have obeyed the law. I chose this next equation because it's a great example of one of the other techniques you need when balancing. We still want to start the exact same way. Begin balancing with atoms that are found only once on each side in different amounts. So that's why I've chosen the arsenic in this case. And we are going to balance the equation. Now, is the arsenic really in different amounts? Again, yes, because over here on the product side, notice this is another one of those things in parentheses. What are those called? Polyatomic ions. Arsenic trioxide, also known as rat poison, not a great chemical to have around. And there are 3 arsenic trioxides attached to the aluminum. So how many arsenic are there on the right-hand side? Okay, well, it's inside the parentheses, and there's a 3 outside, so it's 3 times the 1, 3 arsenic. So if I want to have 3 arsenic on both sides, what coefficient do I need? Over here, I need a coefficient of 3. That brings the arsenic into alignment. Next, let me do the aluminum. Let's see, the aluminum is found once on each side. Here's the aluminum, and here's the aluminum. So what do I need? What coefficient do I need? Oh, wait a second. There's nothing I can do with the aluminum. Why? Because it's already in the same amounts on both sides. If it's in the same amounts on both sides, what can you possibly do to it? You just leave it alone. So what's the next thing I want to deal with? Well, let's see. Let's deal with the hydrogen now. Hydrogen's a good one. On the left side, notice we've got 3 hydrogen, 3 times 1. On the right side, we've got 2 hydrogen. So let's see, what can I multiply 2 by to get 3? Obviously, that's not going to happen, not with any whole number. So this is where we run into our next technique that we need quite a lot when balancing chemical equations, that I call the odd-even technique. If you have an odd number of a chemical on one side of an element and an even number of that same element on the other side, well, the only way out of that situation is to make the odd side even. If you make the odd side even, well, then you can match them up. You can never make an even number become odd, but you can make an odd number become even, usually just by doubling it. So look at the one on the left. That actually has more hydrogen, yet that's the one I'm going to double. It seems crazy, but this is the way out of problems you get when balancing equations. If I double the 3, Now making it a 6, well, now it's going to be possible to balance this equation. That gives me 6 hydrogen. Well, how can I make the right side 6? What do I have to multiply H2 by to have 6 hydrogen? I need a coefficient of 3 in front of the hydrogen. Notice the only problem is, guess what? I just threw off the arsenic. We had already balanced the arsenic with the previous coefficient. Now we just doubled it. So now how many arsenic do we have on the left side? We have 6 arsenic. On the right side, we still only have 3. Notice the polyatomic ion multiplied by 3. So what coefficient do I need in order to balance the arsenic? I need a coefficient of 2 in front of the aluminum arsenic trioxide. Okay. The only problem there is, guess what? I just messed up that aluminum that I was pointing out before that was already balanced to begin with. So now I've gone and messed up that aluminum that was originally balanced. So how can I bring the aluminum back into alignment? How can I match up the aluminum on the left? The great thing is that is a pure element. Whenever there's a pure element, it's a safety valve. It gets you out of any situation that you're stuck in because you can tamper with that. It doesn't mess with any other chemical. So I simply have to put a coefficient of 2 in front of the aluminum. Now that gives me 2 aluminum on the left, 2 aluminum on the right. 6 hydrogen on the left, 6 hydrogen on the right. 6 arsenic on the left, 6 arsenic on the right. That's hard to see. Oh yeah, but what about the oxygen? Oops, we didn't check the oxygen. Well, 6 times 3 gives me 18 oxygen on the left. And then over here, this is tricky. The arsenic trioxide has 3. And then there's a 3 outside the parentheses, that's 9. And then 9 times 2 is 18. So look, the oxygen balanced itself. When we were balancing everything else, the oxygen just came out in the wash, as they say. So this is indeed balanced. I was getting a little ahead of myself there, but luckily it didn't matter because the oxygen had already been balanced indirectly. So this is how you use the odd-even technique. If you ever have an odd number on one side and an even number on the other, you make the odd side even. Usually that's doubling it. Sometimes you have to multiply it by 4, but usually it's doubling it. That's the only way out of that situation, and then you can get a balanced equation. Some things you see in a chemical equation do not affect balancing at all. Things like lowercase letters in parentheses, those are not polyatomic ions. That just means solid, liquid, gas. What's the fourth state of matter? Oh yeah, plasma. So it could be that as well. AQ means aqueous. That's the Latin word aqueous. Comes from the Latin word for water. It just means that it's floating around in water. It's in solution. The yield sign, well, that's important because that shows you the middle. The yield sign shows you where to balance around on the two sides. That separates the two sides. But sometimes it looks like this. It's going both ways. Well, that means the reaction is reversible, but that still does not affect balancing. The two sides still have to be balanced. If you have something written above the yield sign, that might indicate the conditions necessary for the reaction to take place, like electricity or heat, something like that. Sometimes we write catalysts above the yield sign as well. The reaction might not happen without that catalyst. Or we could put the catalyst on both sides of the equation. We could show it on both sides. It just wouldn't be changed by the chemical reaction. None of these things affect balancing. You can pretty much ignore them. The only thing I would say that's critical is realizing that, well, the yield sign is the middle. You balance on the two sides of that, whether it looks like that one or one of these, like a double one going both ways. You still balance the two sides of that arrow, that yield sign. So in this equation, what you see is the reactants. One of them is aqueous. Notice right there, the AQ, that means it's in water. And then some of the products are aqueous. They're in water. Okay, so that means that while this reaction is going on, a whole bunch of these chemicals are all floating around together. So if you want to picture it in your mind, think of all of those as being together in one big aqueous solution. And then of course, water is also a product, but you know what? If you have an aqueous solution, filling a beaker up to 480 milliliters, and then you produce a little more water and it goes up to 481 milliliter, you might not even really notice that water that is produced by this reaction. It's a little tricky to notice water that is produced in an aqueous solution. Another thing shown on this equation is below this. You can see the reaction of nitrogen with hydrogen producing ammonia. This is the synthesis of ammonia. And you notice that it needs certain conditions, a certain temperature, and a certain pressure. This is a pressure for this to take place. It doesn't just start on its own. It needs those conditions to get started, and then you can produce ammonia, NH3. This is, of course, a balanced equation, although you don't want to assume that just because somebody's thrown in coefficients, don't assume they're all right. You always want to double check for yourself. So notice that this is 3 times 2, that would be 6 hydrogen. Over here, 2 times 3, that would be 6 hydrogen. Over here we've got 2 nitrogen, and over here 2 times 1, that's 2 nitrogen. Good, it is balanced. Notice that all 3 of these chemicals, both reactants and the product, are a gas, are in the state of a gas. Later, we are going to incorporate the reaction types. I've already mentioned at least 1 or 2 of them in this, but understanding reaction types gives you the language we need to talk about chemical equations. So I was already talking about combustion, but you know there's 4 others. So when we're talking about an equation, we want to use the right language, and that's a pretty easy thing to learn. That'll be the next one. Another thing we don't want to forget is how to calculate a mole of a chemical using its molar mass. This is which we like to get in chemistry. We like to get quantitative and give numbers. This is what gives numbers to chemical reactions. So we will be still using all the things we learned about molar mass and moles in the future in stoichiometry coming up soon.